In the previous videos, we have studied electrostatic fields and magnetostatic fields. That means the study of static electric fields and study of static magnetic fields. Now, slowly we will be moving towards time varying fields, because in real-time applications, in case of telecommunication engineering, wave propagates in the form of electromagnetic wave. So electromagnetic wave, it is basically a time varying electric and magnetic fields. So having knowledge of static electric fields and static magnetic fields, now we will explore the study of time varying electric and magnetic fields. So we have seen a stationary charge Q, it produces electrostatic fields. So we have seen the corresponding equations, how the stationary charge Q, it produces electric field intensity E or electric flux density D. In the same manner, the static magnetic field, it is produced because of a steady current. So we have seen earlier, because of a steady current flowing through the conductor, how the magnetic field is produced, and we have seen how to find out the expressions for the magnetic field intensity and the magnetic flux density B. Now, as I discussed, we are going to study time varying fields. So those are called as electromagnetic fields. For example, in most of the practical applications like communication, the signal propagates from one point to the other point in the form of electromagnetic wave. So in electromagnetics, we must know how the electric fields and the magnetic fields, they vary together. So that is a study of time varying fields. So if we assume some antenna here and some current is supplied to this antenna, and this current, it will be a sinusoidal current, that means time varying current. So this time varying current, it produces electromagnetic wave here. So this electromagnetic wave, it propagates through the space. So now onwards, we will be studying how this electromagnetic wave propagates through space. That is uniform plane wave propagation. That is the last topic in this subject. So before that, we will study what are the basic properties of this electromagnetic wave, how this time varying electric and magnetic fields are produced. So let us start with Faraday's law. As per Faraday's law, the EMF induced in a conductor is equal to rate of change of the flux cut by that conductor. And the negative sign, it is as per Lenz's law. So the negative sign represents that the direction of the EMF induced, it opposes the cause producing it. So we'll begin our theory with this statement of Faraday's law. So in a closed circuit, the EMF is produced if there is a rate of change of flux. And this phenomena is called as electromagnetic induction. So when a closed path moves in a magnetic field, so there may be magnetic field here, and if this closed path is moving in a magnetic field, EMF is induced in this closed path. So this is called as electromagnetic induction. Now, as per Faraday's law, just now what we have seen, the EMF induced is minus d phi by dt. For EMF to be induced, it is essential that the rate of change of flux, it should be a non-zero value. And this rate of change of flux we may get because of any one of the situations. Like, for example, the flux associated with this path, it may be changing, but this path is stationary. The second possibility is there is a relative motion between the stationary flux and this closed path. Third possibility is the combination of the two. That means the flux B, it is also time varying or time changing, and the path, closed path, it is also moving. So that is case 3. Now we'll write the equations corresponding to all these 3 possibilities. That means flux is changing, path is stationary. In the second case, flux is stationary and the closed path is moving. And case 3 is combination of the two. So let us proceed. Now before that, let us see what is the statement of Lenz's law. So Lenz's law gives us the justification for this negative sign. So EMF induced is negative rate of change of flux. So this is because, as per Lenz's law, the direction of the induced flux is such that it opposes the cause producing it. That means the changes in the magnetic flux, where here n is the number of turns in the circuit. Now in the earlier chapters we have seen the EMF induced, it is given by negative line integral E dot dl around the path. Now as per equation number 1, the EMF induced E, it is minus d phi by dt. Now here phi is the flux. We have seen earlier the flux passing through the surface can be evaluated by surface integral B dot ds. So substituting this phi in this equation, we can write this as minus d dt surface integral B dot ds. So based on this, I can write equation for EMF induced as integral E dot dl equal to minus d dt. So this is substitution for flux phi. So this is surface integral B dot ds. Now let us consider the case number 1, where there is a closed path here which is associated with the time varying magnetic flux density. So the magnetic flux density B here, it is a function of time. So that means, or in other words, I call it as the time varying magnetic flux density, whereas the closed path, it is stationary. Here, so it will produce EMF because there is a rate of change of flux. As per this equation, Faraday's equation, we have seen E is equal to minus d phi by dt. So as the flux density is a function of time, so that's why there is some rate of change of flux here. So because of that, EMF is induced here. So as per our equation number 4, just now what we have written, the EMF induced, it is E dot dl, and by substituting phi as surface integral b dot ds, just now we have seen. So this is actually phi here, minus d dt minus d phi by dt. Now we'll apply Stokes theorem to convert this line integral into surface integral. Applying Stokes theorem, line integral E dot dl, we can write it as surface integral curl of E dot ds equal to minus surface integral dv by dt dot ds. Now both sides are surface integrals here, so we can equate the quantities inside the surface integral, and this ds it will cancel on both sides. So equating the quantities inside the surface integral, this is a del cross E, that is the curl of E dot ds equal to minus db by dt dot ds. Now this ds I can cancel on both sides, so this gives me curl of E is equal to minus dB by dt. That means curl of E is equal to negative rate of change of magnetic flux density. So this is also one of the Maxwell's equations for time varying fields. So as we have seen, curl of E is equal to minus dB by dt, that is rate of change of flux. Now if the flux density B, if it is not function of time, or in other words it is stationary, so in that case the rate of change of flux density, it will be 0. So this equation we can write as curl of E is equal to 0. So this happens in case of static fields. So in case of static fields, E dot dl, line integral E dot dl is equal to 0 and curl of E is equal to 0, because for stationary fields rate of change of flux density is 0. Now let us move to the next case where the magnetic field here, it is stationary or uniform and the closed path is moving. So in this situation the EMF induced, it is called as dynamically induced EMF or motional EMF. So here we assume it's a rail of conductors. So this is one conductor, this is another conductor which are parallel to each other, so we call it as the rail of conductors. And this is a sliding bar, this is the sliding bar which is sliding or moving on the rail of conductor in y direction, and the length of this bar, it is d. Length of this bar, it is d. So at this point x is equal to 0, and at this point x is equal to d. So this means the distance between these two rails, it is d, or the length of this bar, it is d, and this bar, it is moving in direction y, and the flux density is uniform here. So let us find out the equations for the EMF induced in this case. So as per Lenz's law, the EMF induced, it is the proportional to the rate of change of flux. Now in this case, to find out the rate of change of flux, we must know how much is the flux cut by this bar when this bar is moving in y direction. Now as we have seen, the length of this bar, it is d, and this bar, it is moving in y direction. So if this bar moves a distance of y, the area covered by this bar, it will be y into d, because d is the distance of this bar. So this area multiplied by the flux density, that will give me the total flux passing through this surface or the area at any time. So phi is equal to BYD. Now as per Faraday's law, the EMF induced is minus d phi by dt. Now let us substitute this BYD here, which is the flux cut by this bar when it is moving in the y direction. Now here B and D, these are constants with respect to y. So after substituting this phi here, this becomes minus B dy by dt d. Now this dy by dt, it is nothing but v. That is the velocity of this conductor when it is moving in y direction. So this is equal to v. V is the velocity with which the conductor is moving in the y direction. So the equation for EMF induced, it reduces to minus BVD. Now we know the force on a charge Q when it is moving at a velocity v in a magnetic field, it is given by F equal to Q into V cross B, where V, it is the velocity with which the conductor is moving and B is the corresponding magnetic flux density. So if I rearrange this equation as F upon Q, so we know F upon Q, it is nothing but force per, it becomes force per unit charge, or in other words we call it as the electric field intensity. So in this case F upon Q, we call this as the electric field intensity, that is, and this electric field intensity, it is produced because of the motion of the conductor. So that's why we call it as the motional electric field intensity. We represent it by subscript EM. So EM, that is the motional electric field intensity, we can write it as V cross B, where V, it is the velocity of the conductor and B, it is the stationary magnetic flux density. Now we have seen earlier the EMF induced, it is E dot dl. Now in this case, this E is nothing but the motional electric field intensity. So now the EMF induced, motional EMF induced, I can write it as integral EM dot dl, and we have seen EM is equal to V cross B. So substituting EM as V cross B, I get this as integral V cross B dot dl. Now for EMF to be induced, it is necessary that this last equation have a non-zero value, and this is possible only on the portion of the path which is in motion. So portion of this conductor which is in motion in y direction with a velocity v. Now this equation integral V cross B dot dl, which is the motional induced EMF, we can simplify this over the given area. If this conductor moves in this direction by a distance of y, then this may be this total area. Now V, that is the velocity, and B, both are perpendicular to each other. So the cross product V cross B, we can write it as V into B, magnitude of V into magnitude of B. This integral, it is over the length of this conductor. That means from x equal to 0 to x equal to d. So the limits are now 0 to d. So as v cross b is equal to v into b, and dl, now this integration, it is in the x direction. So this dl, I can write it as dx. So v and b, this we can take outside of this integral. Now integral 0 to d over the length dx, so that is nothing but d. So if v and b are perpendicular to each other, that means the velocity and the magnetic flux density, if they are perpendicular to each other, then the expression for EMF induced, it reduces to b v into d. So this is about the EMF induced if magnetic flux density is uniform and the path is moving. Now in situation 3, the closed path, it is also moving, and the flux density B, it is also time varying. Then in that case, the total EMF induced, it is because of both situations. So that means the transformer EMF plus the motional EMF. So that is combination of case 1 and case 2. So this is about the Faraday's law. So we have discussed 3 cases where the path is stationary and the flux is time varying. In the second case, flux is stationary and the path is moving. And in the third case, the closed path, it is also moving with a velocity v, and flux is also time varying.